Hello and welcome. If you're prepping for an electronics exam, you are in the right place. We are about to take a guided tour through some of the smartest components in electronics, special amplifiers. Now, these aren't your typical amps for just making things louder. Nope. These are the brains behind things like noise-canceling headphones and the muscle inside heavy industrial controls. Think of them as precision tools, each one designed for a really specific, clever job. Let's get started. So here's our game plan. We'll start with what even makes an amplifier special. Then we'll dive into the differential amp, move on to the super versatile operational amplifier, or op-amp, see it in action, and then wrap things up with the powerful magnetic amplifier.
Okay, first stop. Let's get the big picture down. What exactly are special amplifiers?
We all kind of get what a regular amplifier does, right? Think of a guitar amp or a stereo. It takes a small signal and makes it bigger, makes it louder. That's it. But a special amplifier, that's a whole different ballgame. It's not just about power, it's a precision instrument designed to perform a very specific and often pretty complex task.
And this really lays it all out. A standard amp's goal is just raw power, more volume. But a special amplifier, its goal is to do something smart. Like comparing two different signals to see what's different, or adding multiple voltages together. Their names actually tell you what they do, which is a huge clue.
So let's look at our first major concept. Meet the differential amplifier. And a great way to think of this guy is as a difference detector.
Okay, so here's the official definition, straight from NEET's Module 8. The key word here, the one you absolutely need to remember, is difference. This amplifier doesn't really care how big the input signals are on their own. It only cares about how different they are from each other.
Now, I know this circuit diagram might look a little intimidating at first, but don't worry about all the parts. Just focus on this. See the two inputs on the left? They feed into the circuit, and the circuit's whole job is to look at both of them and say, okay, what's the difference? That difference is what controls the signal that comes out on the right.
That quote from the source sounds super technical, right? But base-to-emitter bias is really just a fancy engineering term for the voltage difference between those two inputs. So, if input 1 is, say, 3 volts, and input 2 is 2 volts, the circuit just sees that 1 volt difference, and that's what it amplifies. So, why do we care? What's the big deal? Well, this thing is an amazing noise-canceling machine. See, in the real world, a lot of unwanted electrical noise or interference tends to hit both signal wires at the same time. The differential amp sees that identical noise on both inputs, calculates the difference, which is 0, and just completely ignores it. That amazing trick is called common mode rejection.
And this shows that idea perfectly. Look at the picture on the left. The two inputs are opposites of each other. They're way different. So you get a big amplified output. Now look at the right. The two inputs are exactly the same. They're common. The amplifier sees 0 difference, and what's the output? A flat line. Nothing. The noise just vanishes.
All right, now let's build on that idea. Our next stop is the operational amplifier, or as everyone calls it, the op-amp. And if the differential amp is a specialized tool, the op-amp, well, it's the Swiss Army knife of electronics. It's incredibly versatile. According to our source material, there are 3 things that really make an op-amp what it is. 1, it has crazy high gain, meaning it can amplify a signal by a massive amount. 2, it has very high input impedance. Think of it like this. It's a really polite listener. It doesn't draw much power from whatever signal you're feeding it. And 3, very low output impedance, so it can easily drive the next stage of the circuit with its new, powerful signal.
And here it is, the aha moment. Take a look at this block diagram of what's inside an op-amp. What's that very first block on the left? It's a differential amplifier. It's the exact same circuit we just finished talking about. This is how electronics works. These concepts stack on top of each other. You master the differential amp, and you're already halfway to understanding the op-amp.
So, what can you do with this amazing Swiss Army knife? Well, one of the coolest things is you can use op-amps to build circuits that, literally, do math. Check out this circuit, for instance. It's called a summing amplifier, and just like the name says, it takes a couple of different input voltages, adds them all together, and gives you one single output. And the math is just beautifully simple. Let's say you put positive 3 volts on the first input and positive 4 volts on the second. The circuit just adds them up and spits out negative 7 volts. Now, that negative sign is just a quirk of this specific setup, but the point is, it's a tiny little calculator you can build with just a few parts.
All right, for our last stop, we're going to switch gears from tiny calculations to some serious heavy lifting. Let's talk about the magnetic amplifier, a real rugged workhorse.
A magnetic amplifier, or mag-amp, is kind of like a really smart, controllable transformer. It uses this special iron core that you can saturate with a magnetic field. By putting in a small little DC control signal, you change how saturated that core is, and that acts like a valve controlling how much big, heavy-duty AC power can flow through. It's kind of like controlling a giant fire hose just by turning the tiny knob on a garden hose.
Now, it's not the right tool for every job. You can see it's got some big advantages. It's super rugged, reliable, and efficient. That's why you see them in heavy industrial stuff or on ships. But the trade-off is that it's slow and not great with fine details, so you'd never find one in a high-end stereo. It's all about brute force power control, not delicate signals.
Okay, that was a whirlwind tour of 3 really important special amplifiers. Now, to help all that sink in and get you ready for your test, let's do a quick rapid-fire review and a couple of practice questions.
Let's lock this stuff in. Ready? Differential amp amplifies the difference. Common mode rejection cancels out noise. Op amp, the versatile building block. Summing amp adds voltages, and the magnetic amplifier controls heavy power. You got this.
All right, first practice question. You've got 2 identical signals going into a differential amplifier. What's going to come out the other side? Think about that common mode rejection we talked about.
And the answer is 0. That's right. Because the signals are identical, there's no difference for the amp to amplify. The common signals are rejected. Nice.
Okay, question number 2. What were those 3 key things that make an op-amp an op-amp?
And there they are. Very high gain, very high input impedance, and very low output impedance. Remember those 3, and you've got the essence of what makes an op-amp so useful.
So let's end with this thought. These things we talked about, they aren't just abstract ideas for a test. They're the real-world building blocks inside everything from audio mixers and medical sensors to industrial power grids. Now that you know how they work, what kind of systems do you feel like you could start to tackle? Good luck with your studies.